An aircraft plunged toward the Appalachian Mountains with both engines dead. 76 passengers screamed. Then a cold woman in seat 12F stood up calmly. "I can land this," she said. Her call sign, Viper. She wasn't a pilot, she was something far more dangerous. Before you watch full story, comment below from which country are you watching. Don't forget to subscribe for more amazing stories. Dr. Helena Voss looked like every other business traveler in first class. Charcoal gray blazer. Black turtleneck. Tailored pants that probably cost more than most people's monthly rent. Designer glasses perched on her nose. Dark hair pulled back in a sleek, low bun. The kind of person you see and immediately forget. She sat in seat 12F on United Express Flight 4422, Charlotte to Pittsburgh, working on her laptop with Bose noise-canceling headphones blocking out the world. Her screen showed complex mathematical equations, lines of code, and 3D aircraft models rotating in simulation software. To anyone glancing over, it looked like boring technical work. The businessman in seat 12E had tried making conversation during boarding. He was a friendly middle-aged man in an expensive suit, probably a sales executive or regional manager heading home after a conference. "What do you do?" he'd asked with a warm smile, hoping to pass the flight with pleasant conversation. Helena had looked at him for exactly 1 second. Her eyes had met his briefly, showing no emotion, no warmth, no acknowledgement of his attempt at human connection. Then she'd returned to her screen without answering. Without a smile. Without even a polite nod. He hadn't tried again. When the flight attendant came by with the beverage service before takeoff, Helena had held up one finger without removing her headphones or looking up from her work. The attendant, experienced with difficult first-class passengers, had brought water without asking for clarification. Helena had nodded thanks without making eye contact and immediately went back to work. "No, thank you." No smile. Just a mechanical acknowledgement. The flight attendant had whispered to her colleague, "Cold as ice, that one." To the 75 other people on this Embraer E-175 regional jet, Dr. Helena Voss was just another cold tech executive who thought she was too important for human interaction. The kind of person you see in first class and immediately dislike. Arrogant. Self-important. Too busy to acknowledge that other human beings existed. Nobody knew what she was actually working on. Nobody knew the equations on her screen were calculating stall recovery angles for asymmetric thrust scenarios. Nobody knew she was running simulations of aircraft failure modes, testing theoretical recovery procedures for disasters that never happen. Nobody knew that the rotating 3D model on her screen was an F-22 Raptor in an uncontrolled spin at 40,000 feet, and she was calculating the exact control surface inputs needed to recover. And absolutely nobody knew that in 42 minutes, she would be the only thing standing between them and death. Helena worked in complete silence, her fingers moving across the keyboard with practiced precision. She was reviewing code she'd written 6 years ago, emergency flight control algorithms designed for fighter jets experiencing catastrophic system failures. The code had been used in 17 real-world emergencies. 16 pilots had survived because of it. One hadn't. She pushed that thought away and continued working. Helena Voss had never wanted to be a pilot. She wanted to be something better. Something more useful. Something that would actually save lives. At MIT, at age 22, she'd written her PhD dissertation titled Non-Standard Flight Control Recovery Protocols for Catastrophic Multi-System Failures. It was 347 pages of detailed mathematical analysis, computer simulations, and theoretical procedures for recovering aircraft from situations that should be unrecoverable. Her thesis was brilliant work. Her advisor, Professor Richard Chen, had called it brilliant but useless. "Helena, you're designing recovery procedures for failures that never happen," he told her during her defense. "Modern aircraft have so many redundancies, multiple hydraulic systems, backup electrical systems, dual engines, fly-by-wire computers with triple redundancy. Your scenarios are theoretical fantasy. You're solving problems that don't exist. Helena's response had been calm and precise, delivered in the same cold, analytical tone she used for everything. Then why do pilots still die when multiple systems fail simultaneously? Because they're trained for single failures, not cascading catastrophes. The Boeing 737 MAX crashes happened because pilots weren't trained for a scenario where multiple systems failed in combination. Air France 447 crashed because pilots didn't know how to recover from a stall when their airspeed indicators failed. I'm designing protocols for when everything goes wrong at once. Her advisor had frowned. Helena, the statistical probability of multiple simultaneous system failures is non-zero, Helena interrupted. Which means it will happen eventually. And when it does, pilots will die unless someone has thought through the recovery procedures. The academic committee had been split. Half thought she was wasting her talent on unrealistic scenarios. Half thought she was onto something important. They'd approved her dissertation with reservations. But the Air Force hadn't had any reservations. Lockheed Martin's Skunk Works, the legendary advanced development program that designed the State Route 71 Blackbird, F-117 Nighthawk stealth fighter, and F-22 Raptor, had offered her a job within 24 hours of her defense. "We need someone who thinks like you," the recruitment officer had said. "Someone who designs for worst-case scenarios. Because in test flying, worst-case scenarios happen every day. We push aircraft to their absolute limits. Sometimes beyond their limits. We need someone who can figure out how to recover when everything goes wrong." For 12 years, Dr. Helena Voss became the civilian contractor that fighter pilots both feared and worshipped. Her official job title was Failure Systems Specialist. Her real job was simple: embed with F-22 squadrons and teach pilots to recover from aircraft failures that should be unrecoverable. Her method was terrifying. She would create computer simulations of catastrophic failures, scenarios where multiple systems failed simultaneously in ways that should kill everyone aboard. Then she would calculate theoretical recovery procedures using physics, aerodynamics, and mathematics. Then, and this was the part that terrified pilots, she would fly in the back seat of real fighter jets while test pilots attempted her theoretical recovery procedures. She flew 340 test flights over 12 years. Sitting in the back of F-22 Raptors, F-35 Lightning IIs, F-15 Eagles, even old F-16 Falcons when the Air Force wanted to test if her procedures worked on older aircraft. She would sit in the back seat while pilots deliberately broke their aircraft. Shutting down hydraulic systems at Mach 1.8. Cutting fly-by-wire computer power at 40,000 feet. Creating asymmetric engine thrust at high angles of attack. Jamming flight control surfaces in extreme positions. Inducing multiple simultaneous system cascades that should have killed everyone aboard. Helena would sit calmly in the back seat, monitoring data streams on her ruggedized tablet computer, while the aircraft shook and screamed and tried to fall out of the sky. The pilots in front of her would be fighting the controls, sweating, sometimes swearing, sometimes praying. And Helena's voice would come through the intercom, calm as someone ordering coffee, asymmetric flap deployment at 15 degrees. Differential spoiler on the left wing. You'll get 8 degrees of roll authority. Use it. The pilots would follow her instructions. Doing things that weren't in any flight manual. Things that violated every standard procedure they'd ever learned. Things that seemed insane. And the aircraft would recover. Her call sign, Viper, came from her personality, not her appearance. Cold-blooded. Precise. Venomous when questioned. Emotionless under pressure. Deadly when she needed to be. Pilots who worked with her had a saying: Viper's simulations will kill you in training so you survive in combat. She published 19 patents on emergency flight control algorithms. Her work was embedded in the flight computers of every F-22 and F-35 in the United States Air Force. Software that ran in the background, monitoring for failures, ready to provide recovery suggestions when multiple systems failed. Pilots called it Viper mode, when their aircraft got so broken that the computer started suggesting Helena's insane recovery procedures. She understood aircraft better than the people flying them. She could look at an aircraft schematic and immediately identify potential failure points. She could watch an aircraft in flight and calculate its exact aerodynamic state just from visual observation. She could feel turbulence patterns and predict weather conditions. But Helena was never a pilot herself. She'd never wanted to be. She didn't need to be. Pilots flew by instinct and training. Helena flew by mathematics and physics. She was better than them because she understood the fundamental forces at work. Lift. Drag. Thrust. Weight. Control authority. Stall characteristics. Everything could be calculated. Everything could be predicted. Until Test Flight 341. Edwards Air Force Base, California. 2 years ago. Morning of March 15. Helena arrived at the flight line at 0600 hours, carrying her tablet and wearing the same professional clothes she always wore. She refused to wear a flight suit, insisting she was a civilian contractor, not military personnel. She was scheduled for Test Flight 341 with Major Ryan Torch Mitchell, one of her best students. Torch was an exceptional pilot, calm under pressure, precise in his control inputs, willing to trust Helena's insane instructions even when every instinct told him not to. The test plan was ambitious: simultaneous hydraulic and electrical failure at high altitude. Helena had designed a recovery protocol that used aerodynamic forces alone, no powered flight controls, no computers, just pure physics and pilot skill. The briefing took 90 minutes. Helena explained every detail with her characteristic precision. At Angels 38, we'll simulate total hydraulic failure in all 3 systems. Simultaneously, we'll cut main electrical power. Your flight controls will be locked. You'll have zero authority through normal means. Torch had nodded, studying the briefing materials. And the recovery? Asymmetric thrust vectoring combined with differential drag. You'll use engine power differences to create rotation. Left engine to 90%, right engine to idle. The thrust differential will yaw the aircraft. We'll use that yaw to induce roll. Once rolling, we deploy flaps asymmetrically to create lift differential. That lets us control pitch. Another pilot observing the briefing had raised his hand. Dr. Voss, that procedure isn't in any manual. Helena's response was ice cold, because no one else has thought of it. That's why I'm here. The test began normally. Torch flew the F-22 to 38,000 feet over the California desert. Helena sat in the back seat, monitoring systems. Everything was perfect. Clear weather. Unlimited visibility. Empty airspace for hundreds of miles. Ready when you are, Viper, Torch said. Initiating test in 3, 2, 1, mark. Helena triggered the test sequence from her tablet. Hydraulic systems began shutting down in sequence. Electrical systems started failing. And then something went wrong. The simulated failure became real. An actual hydraulic line ruptured in the right wing. Not a computer simulation, real hydraulic fluid spraying into the internal structure. The fluid hit hot engine components and ignited. Fire warning lights illuminated across the cockpit. The aircraft became uncontrollable at 38,000 feet. The stick went dead in Torch's hands. The F-22 started tumbling, rolling uncontrollably, the nose dropping, the aircraft entering a flat spin. Helena watched her instruments. Watched the altitude unwinding. Watched the rotation rate increasing. Did the calculations in her head. They had 90 seconds before the spin became unrecoverable. After that, ejection would be the only option. Her voice came through the intercom, calm as ever, no hint of fear or urgency, asymmetric thrust. Left engine to 90%, right to idle. Differential flap configuration Alpha 7. Torch's hands were shaking, but his execution was perfect. He followed Helena's commands exactly. Left throttle forward. Right throttle back. Flaps asymmetric. Nothing happened for 3 seconds. Then the aircraft's rotation began to slow. The nose started rising. The flat spin transitioned to a normal spin. The normal spin transitioned to a steep descent. The steep descent transitioned to controlled flight. At 22,000 feet, Torch had full control again. They landed safely at Edwards. Helena climbed out of the aircraft and walked directly to the debriefing room without speaking to anyone. She didn't celebrate. Didn't acknowledge the other pilots congratulating Torch. Didn't show any emotion. But the NTSB investigation that followed revealed something that destroyed Helena's career. The hydraulic failure wasn't random. It wasn't a manufacturing defect. It wasn't bad maintenance. It was caused by Helena's test protocol pushing the system beyond its design limits. The hydraulic pumps were only rated for certain pressure ranges. Helena's test sequence had commanded them to operate at 115% of maximum rated pressure. The line had ruptured because she deliberately overstressed it. She'd been so focused on testing recovery from worst-case scenarios that she'd created the worst-case scenario. The Air Force Safety Investigation Board's conclusion was brutal. Dr. Voss's test protocols are unnecessarily dangerous. Her pursuit of theoretical knowledge endangers pilots and aircraft. While her recovery procedures are technically sound, her method of testing them creates unacceptable risk. Her contract is terminated effective immediately. Helena tried to defend herself at the hearing. She stood before a panel of generals and safety officers and made her case with characteristic precision. We need to test extreme failures. Pilots die because they don't know how to recover from scenarios that should be impossible. If we only test normal failures, we only learn normal recoveries. I'm teaching pilots to survive impossible situations. A general interrupted her. Dr. Voss, you nearly killed one of our best pilots. You created a real emergency to test your theoretical recovery. That's unacceptable. You're brilliant, but you're reckless. You're done. They stripped her security clearances that day. Revoked her access to all military bases. Ended every contract. Deleted her computer access. Escorted her off Edwards Air Force Base by armed security. For 2 years after that, Helena worked as a consultant for commercial aviation companies. Boeing. Airbus. Regional carriers. Boring, safe, corporate work designing minor software improvements and reviewing maintenance procedures. She hated every minute of it. She missed the test flights. Missed the edge of disaster scenarios. Missed teaching pilots to survive the unsurvivable. Missed sitting in the back seat of an F-22 while it tried to kill them, calmly calculating recovery procedures. But today, sitting in seat 12F on a routine regional flight from Charlotte to Pittsburgh, she was about to get one more chance to prove her theories weren't reckless. They were necessary. 42 minutes into the flight. 29,000 feet over the Appalachian Mountains. Helena was reviewing simulation code when she heard something wrong. Most passengers wouldn't have noticed. The flight was smooth. No turbulence. The cabin was quiet except for normal conversation and the steady hum of jet engines. But Helena noticed. The engine sound changed. Not dramatically. Not obviously. Just a subtle shift in frequency, the left engine's pitch dropped by approximately 240 Hz. A change so small that it was almost imperceptible. She removed her headphones slowly and listened carefully. 15 seconds later, the right engine's pitch changed identically. Same frequency drop. Same subtle roughness in the sound. Helena's engineer brain immediately began calculating. Synchronized engine degradation. Both engines experiencing the same problem at almost the same time. That ruled out mechanical failure, the probability of two separate mechanical failures occurring simultaneously was statistically negligible. Fuel contamination. Both engines drawing from the same contaminated fuel tank. She needed to confirm. Helena opened her laptop camera app, a trick she'd learned during test flights. She used it as a mirror to watch the wing through her window without turning her head and attracting attention. The left engine's exhaust was visible through the camera. Normally, jet exhaust is nearly invisible, just heated air causing distortion. But this exhaust was darker than normal. Particulate matter was visible in the stream. Small dark specks in the otherwise clear exhaust. Fuel contamination confirmed. Helena did rapid calculations in her head. Contaminated fuel would clog fuel filters. Reduced fuel flow. Engine thrust degradation. Eventually, complete flame out. Based on the rate of degradation she was observing, both engines would fail within 90 to 180 seconds. She closed her laptop calmly. Removed her headphones and placed them carefully in her bag. Zipped the bag closed. Put her laptop in sleep mode. And waited. The businessman in 12E noticed her movements. Everything okay? Helena didn't answer. She was counting seconds in her head. Calculating exactly when the failures would occur. 63 seconds later, it happened. The left engine flamed out. The smooth hum cut off abruptly. The aircraft shuddered violently as asymmetric thrust threw it off balance. Passengers gasped. Someone screamed. The flight attendant in the galley dropped a coffee pot, which shattered on the floor. The smooth flight became rough instantly. The aircraft yawed left as the right engine tried to compensate for the lost thrust on the left side. 31 seconds after that, exactly as Helena had calculated, the right engine flamed out. Both engines, dead. Complete silence except for wind noise rushing past the fuselage and the sound of 76 people realizing they were about to die. The aircraft was now a glider at 29,000 feet, descending at 2,400 feet per minute toward the mountains below. Helena checked her watch. She calculated their glide ratio, their descent rate, their forward speed, the terrain below, the nearest airports. They had approximately 12 minutes until impact. In the cockpit, Captain Sarah Lynn, 44 years old with 16,000 flight hours across 20 years of flying, stared at the engine failure warnings lighting up every display in front of her. Master warning lights. Engine 1 failure. Engine 2 failure. Low hydraulic pressure warnings. Electrical system degradation warnings. Cabin pressure warning. Every system on the aircraft was screaming for attention. First Officer Marcus Webb, 29 years old with 3,200 hours, still relatively new but competent and well-trained, was already reaching for the emergency checklist. Engine failure. Both engines. Marcus's voice was high and tight with stress. Sarah's training took over. Years of simulator practice. Hundreds of emergency drills. She keyed the radio, Mayday, Mayday, Mayday. United Express 4422, dual engine failure, we are gliding, 29,000 feet, 76 souls aboard, requesting immediate vectors to nearest suitable airport. Marcus was running through restart checklists with shaking hands, his finger moving down the laminated emergency procedure card. Engine 1 restart attempt, fuel selector to alternate tank, ignition to continuous, throttle to idle, nothing. No start. Engine 2 restart attempt, fuel selector alternate, ignition continuous, nothing. Sarah, the engines aren't starting. The fuel is contaminated, the engines won't relight. Sarah scanned her navigation display for airports, her mind racing through options. Nearest suitable field is Asheville Regional Airport, 47 miles southeast. Can we make it? Sarah did the math quickly. Their glide ratio in this aircraft was approximately 12 to 1, 12 miles forward for every mile of altitude lost. At 29,000 feet, that gave them a theoretical glide range of about 58 miles in perfect conditions. But these weren't perfect conditions. They had headwinds. They'd already lost some altitude. They weren't at optimal glide speed yet. "We'll be 8 miles short of Asheville," Sarah said, her voice steady despite the terror coursing through her body. Marcus's face went white. "Then what do we do? Where do we land?" "We find flat ground somewhere and pray." "Sarah." Marcus's voice cracked with panic. "There is no flat ground down there. It's all mountains and forest. Have you looked out the window? It's the Appalachian Mountains. There's nowhere to put this thing down." Sarah's hands were steady on the controls, but her mind was racing through every emergency procedure she'd ever learned. She'd trained for engine failures. Single-engine failures. She'd even trained for dual-engine failures, but always with the assumption that at least one engine would restart, or they'd have enough altitude to reach an airport. Nothing in her training covered this scenario. Dual-engine failure at high altitude with contaminated fuel that prevented restart, over mountainous terrain with no suitable landing areas within glide range. They were going to crash. That was the simple truth. They were going to crash into the mountains and everyone was going to die. But she had to try. Sarah made the announcement, keeping her voice as calm as possible. "Ladies and gentlemen, this is Captain Lin. We have experienced a failure of both engines due to fuel contamination. We are currently gliding and will attempt an emergency landing. Flight attendants, please prepare the cabin for emergency landing procedures. Passengers, please review your safety cards and listen carefully to flight attendant instructions." In the cabin, chaos erupted instantly. People screaming. Crying. Grabbing their phones to record goodbye videos. Parents holding their children. Couples holding hands. Businessmen sitting frozen in shock. A teenager in the back crying hysterically. An elderly woman praying in Spanish. The flight attendants were trying to maintain order, moving through the rows checking seatbelts, demonstrating brace positions, trying to keep their own fear hidden. And in seat 12F, Dr. Helena Voss unbuckled her seatbelt and stood up. The businessman in 12E grabbed her arm. His face was pale, eyes wide with terror. "What are you doing? We need to get in brace position. We're going to crash." Helena pulled her arm free without looking at him. Her voice was completely calm. "Let go of me." She walked toward the cockpit. Steady steps. No panic in her movements. No fear in her expression. She looked like she was walking to a business meeting, not toward the cockpit of a crashing aircraft. A flight attendant blocked her path. The attendant's name tag read, "Jennifer, young, maybe 26, trying desperately to maintain professional composure while fighting back tears. Ma'am, you need to return to your seat immediately and prepare for emergency landing." Helena's voice, when she spoke, carried an authority that didn't match her civilian appearance. "I need to speak to the pilots immediately. I'm a flight systems engineer with emergency aircraft experience. I may be able to help with the situation." "Ma'am, I appreciate that, but the pilots are very busy right now managing the emergency." Helena interrupted, her voice still calm but with an edge of steel. "They're managing the emergency by following standard procedures. Standard procedures will result in terrain impact in approximately 11 minutes. I have knowledge of non-standard recovery techniques that may extend your glide range. I need to speak to them now." Jennifer hesitated. She'd been trained to keep passengers out of the cockpit under all circumstances. But she'd also been trained to use all available resources in an emergency. And something in this woman's eyes, the absolute certainty, the cold calculation, the complete lack of panic, made her hesitate. "Are you really a flight engineer?" "Yes. 12 years with Lockheed Martin. Flight test operations. 340 test flights in failure scenarios." Helena pulled out her phone and showed an ID badge. "Let me help." Jennifer made a decision. She opened the cockpit door. Helena stepped through. Sarah and Marcus both turned to see a civilian woman in business clothes standing in their cockpit doorway. Sarah's first instinct was to order her out. Security protocols, cockpit sterility, they were in the middle of an emergency. "You need to leave." Helena interrupted, her voice clinical and precise. "You have contaminated fuel in both engines. The contamination has clogged your fuel filters and caused flameout in both engines. The engines will not restart regardless of how many restart procedures you attempt. You are currently at 27,400 feet, descending at approximately 2,400 feet per minute. At your current glide ratio of 12:1, you will impact terrain approximately 8 miles short of Asheville Regional Airport. You have 11 minutes and 26 seconds to find an alternative solution." Marcus stared at her with his mouth open. "Who the hell are you?" Helena pulled out her phone and showed them her credentials. A Lockheed Martin Skunk Works ID badge with her photo and name, Dr. Helena Voss, marked, Restricted Access, Flight Test Operations. Security clearances were visible. A contractor ID number. "My name is Dr. Helena Voss. I'm a flight systems engineer specializing in emergency recovery procedures. I spent 12 years designing emergency recovery protocols for F-22 fighter squadrons. I've flown 340 test flights in catastrophic failure scenarios. I hold 19 patents on emergency flight control algorithms that are currently used in every F-22 and F-35 fighter jet in the United States Air Force. And I know how to land aircraft with no engine power." Sarah's jaw dropped. "You're military. Civilian contractor." "I was. They terminated my contract 2 years ago for being too aggressive with test protocols." Helena's voice was completely matter-of-fact, as if she were discussing the weather. "But the procedures I designed are mathematically sound and have been proven effective in real-world scenarios. I can talk you through a landing technique that will extend your glide range and allow you to reach a suitable landing surface. We're following standard emergency procedures for dual engine failure." Helena shook her head. "Standard emergency procedures are designed for dual engine failure with functional hydraulic systems, functional electrical systems, and the possibility of engine restart. You have none of those. Your hydraulic pressure is declining rapidly. You're running on emergency battery backup power. Your fuel is contaminated, so restart is impossible. Standard procedures will result in controlled flight into terrain. You need non-standard techniques developed for scenarios that commercial aviation doesn't normally train for." Marcus looked at Sarah. Sarah looked at her instruments. 25,800 feet. They were dropping fast. Sarah made the hardest decision of her career. "Tell us what to do." Helena moved to stand behind the center console where she could see both pilots and all the instruments clearly. She pulled out her phone and opened a calculation app, quickly entering numbers. Then she keyed the radio, and when she spoke, her voice was transmitted on the emergency frequency that every air traffic controller within 200 miles was monitoring. "All stations, this is Dr. Helena Viper Voss, call sign Viper, formerly Lockheed Martin Skunk Works Flight Test Operations, requesting tactical command authority for United Express Flight 4422. I am assuming operational control of this emergency situation. All civilian and military aircraft in the area, please clear the airspace. I will be conducting non-standard flight control procedures. At Langley Air Force Base, Virginia, 140 miles to the east, Lieutenant Colonel Jake Reaper Morrison was sitting in the 1st Fighter Wing Operations Center, monitoring routine air traffic. When Helena's transmission came through the emergency frequency, Reaper froze in his chair. The operations room went silent. Every controller, every officer, every person in the room stopped what they were doing. "Viper?" Reaper said. "Did she just say call sign Viper?" His operations analyst, a young captain, looked confused. "Sir, that's Dr. Helena Voss's old call sign from when she worked with us. But she was terminated 2 years ago. Her clearances were revoked." "I know exactly who she is and what happened to her," Reaper interrupted. She was my instructor. She taught me emergency recovery procedures that saved my life in combat over Syria. She's the best flight systems engineer the Air Force ever had. Reaper grabbed the radio. What's Viper doing on a commercial flight? The analyst pulled up flight information. United Express 4422. Charlotte to Pittsburgh. Embraer E-175. Dual engine failure. They're gliding over the mountains. Reaper's mind raced. If Viper was using her call sign, if she was requesting tactical command authority, that meant she was about to do something insane. Something that violated every regulation. Something that shouldn't work but would work because Viper's mathematics were never wrong. Get me the alert fighters. Now. Sir, this is a civilian emergency. We don't normally. If Viper is on that aircraft and she's taking command, we need to support her. She wouldn't use her call sign unless the situation was desperate. Scramble F-22s immediately. I want 4 aircraft airborne in 2 minutes. Sir, we need authorization from. I'm authorizing it. Those are my fighters and that's my former instructor up there. Scramble now. Within 90 seconds, 4 F-22 Raptors were screaming down the runway at Langley Air Force Base. Reaper was in the lead aircraft, his wingman Lieutenant Hammer Rodriguez on his right, 2 more Raptors behind them. They hit afterburners and accelerated through the sound barrier, racing toward the Appalachian Mountains. Reaper keyed his radio. Viper, this is Reaper. I've got 4 Raptors inbound to your position. We're 8 minutes out at current speed. What do you need? Helena's voice came back over the emergency frequency, calm, clinical, exactly as Reaper remembered from training flights years ago. Reaper, good to hear your voice. I need visual confirmation of terrain below my current position and identification of any flat surfaces within glide range. I'm going to talk these commercial pilots through an asymmetric control technique to extend their glide range. Reaper felt his stomach drop. Copy, Viper. Be advised, terrain below your position is heavily forested mountains. Multiple peaks above 4,000 feet. No airports within your current glide range. Are you planning to execute Theoretical Protocol 7? Protocol 7. Reaper remembered it from training. An insane recovery technique that Helena had designed for situations where conventional flying was impossible. Asymmetric flight control surfaces. Differential drag. Using the aircraft itself as an air brake system. It had a 30% success rate in computer simulations. It had never been tested on a real aircraft. And it had definitely never been tested on a commercial passenger jet. Affirmative, Reaper. Protocol 7. Never tested it in real aircraft operations. About to find out if my mathematical models were accurate. Reaper's voice carried both fear and reverence. Viper, Protocol 7 has a 30% computer simulated success rate. That means 70% chance of catastrophic failure. Better odds than continued standard glide configuration, which has 0% chance of reaching suitable landing area. These pilots are good. They'll follow instructions. Protocol 7 is their best option. Understood. Reaper out. Reaper pushed his throttles forward. The F-22 accelerated to Mach 1.4. He had to get there in time to help. Helena turned to Sarah and Marcus. Both pilots were staring at her like she'd just announced she could make the aircraft fly by magic. Listen very carefully. I'm going to explain this once, and then we're going to execute it. Time is critical. She pointed to the primary flight display. Standard glide configuration gives you a lift-to-drag ratio of approximately 12:1. That means 12 miles forward for every mile of altitude lost. At your current altitude of 27,000 feet, that gives you a maximum range of 54 miles. Asheville Regional is 62 miles away. You cannot reach it with standard glide configuration. Sarah nodded, her hands tight on the control yoke. Correct. So what do we do? I'm going to teach you to fly at a 16:1 glide ratio by manipulating lift and drag asymmetrically across the aircraft. This will extend your range by approximately 33%, giving you enough distance to reach a suitable landing area. Marcus shook his head. That's physically impossible. You can't change an aircraft's glide ratio without engines. You can if you understand advanced aerodynamics, Helena interrupted. Here's how it works. She pulled out her phone and showed them a diagram she'd drawn years ago for exactly this scenario. Step 1, asymmetric flap deployment. You're going to deploy flaps on the left wing only to 15 degrees. Keep the right wing completely clean, no flaps deployed. Sarah's eyes widened. That will create massive aerodynamic imbalance. We'll roll uncontrollably to the right. Correct. You will experience strong roll tendency to the right. You will counter it with left aileron input, approximately 60% deflection. This creates an aerodynamic configuration where you have increased lift on the left side and increased drag on the left side. The increased lift slows your descent rate. The aileron deflection creates additional drag that would normally cancel the benefit, but, and this is critical, the asymmetric configuration creates a more efficient overall lift-to-drag ratio than symmetric configuration. Marcus was frantically scribbling notes on his knee board. This violates every certification standard. Every flight manual. Every procedure. Step 2, differential spoiler drag. Helena continued as if Marcus hadn't spoken. You will deploy spoilers on the right wing only to 30%. This creates drag on the side opposite your flaps, which serves two functions. It stabilizes the asymmetric configuration and prevents over-rotation, and it creates a controlled slip angle that further improves your glide efficiency. Dr. Voss, we've never flown an aircraft like this. Step 3, landing gear as air brakes. At 5,000 feet altitude, you will deploy landing gear. The drag from the landing gear will significantly slow your forward speed, but by that point you will have already converted your excess altitude into forward distance. You'll be close enough to your landing point that the reduced speed will help you make a controlled touchdown. Helena looked directly at both pilots. What I'm describing is a precise manipulation of the four forces acting on this aircraft: lift, drag, weight, and thrust. You have no thrust, so we're manipulating only lift and drag to optimize your glide performance. The mathematics are sound. The physics are proven. This will work if you execute it correctly. Sarah looked at her instruments. 22,000 feet. 10 minutes to impact if they didn't do something. What are our actual chances? Helena's answer was brutally honest. Computer simulations show a 34% probability of successful landing using Protocol 7. Standard glide configuration shows 0% probability of reaching any suitable landing area. The choice is simple. Marcus's voice was barely a whisper. Have you ever actually done this? In a real aircraft? No. I've simulated it 2,000 times in computers. I've tested individual components of the technique in fighter jets. But I've never executed the complete procedure in a real aircraft, and I've definitely never executed it in a commercial passenger aircraft. There was a long silence. Then Sarah spoke, "We're going to die if we don't try something. Give us the exact procedures. Step by step." Helena nodded. Good. Let's begin. 20,000 feet. Helena's voice was calm and precise. Deploy left flap to 15 degrees. Execute now. Sarah's hand moved to the flap lever. She'd operated this control 10,000 times in her career, always deploying flaps symmetrically on both wings for landing or takeoff. Never asymmetrically. The aircraft wasn't designed for asymmetric flap deployment. She set the lever to 15 degrees on the left side only. The aircraft's response was immediate and violent. It rolled right. Hard. The right wing came up, the left wing dropped. Alarms screamed. The artificial horizon display showed them in a 30-degree bank. We're rolling. We're losing control. Sarah shouted, fighting the control yoke. Helena's voice cut through the panic, still completely calm, expected response. Counter with left aileron input. Approximately 60% deflection. You should feel significant resistance. Hold it steady. The nose will rise slightly in 3 seconds. Sarah pushed the control yoke left, fighting the roll. Her arms were shaking with the effort. The aircraft wanted to roll right, wanted to enter a spiral. She held it with everything she had. Marcus was watching the instruments, his voice high with stress. 35-degree bank, decreasing, 20 degrees, 15. The aircraft stabilized. The roll stopped. And then, impossibly, the nose lifted 3 degrees. Descent rate? Helena asked. Marcus checked his vertical speed indicator. 2100 feet per minute. We're descending slower. How is that possible? Helena's explanation was pure physics. You're creating more total lift with the asymmetric configuration than you had with symmetric clean configuration. The left wing is generating significantly more lift due to the flap deployment. The right wing is generating less lift, but the total is higher. Additionally, the slip angle we've created reduces induced drag. You're flying more efficiently. The physics made no sense to Sarah's pilot instincts, but the instruments didn't lie. They were descending slower. Their glide was extending. 18,000 feet. Maintain current configuration. Check your forward speed and heading. Sarah checked. 170 knots forward speed. Heading 270. Both stable. Good. You're converting vertical velocity into horizontal range. Continue current configuration until 15,000 feet. 15,000 feet. Deploy right spoilers to 30%. Execute now. Sarah activated the spoiler controls on the right wing only. Spoilers were panels that popped up from the wing surface to disrupt airflow and create drag. Normally they were used symmetrically for slowing down or increasing descent rate. But Helena wanted them asymmetrically. The aircraft shuddered as the right wing spoilers deployed. Sarah felt the yaw tendency. The aircraft wanted to turn right as drag increased on that side. Compensate with rudder, Helena instructed. Small inputs. You're looking for stability, not correction. Sarah pressed the left rudder pedal slightly. The aircraft stabilized again. The whole configuration felt wrong. Completely wrong. The aircraft was flying in a state it was never designed for. Asymmetric flaps. Asymmetric spoilers. Constant aileron and rudder input to maintain control. But it was working. Descent rate? Helena asked. Marcus checked again. His voice carried wonder and disbelief. 1,800 feet per minute. We're descending even slower now. Dr. Voss, this shouldn't be possible. Helena's response was matter of fact. It feels wrong because you're flying an aircraft in a configuration that violates every design assumption the engineers made. But physics doesn't care about design assumptions. You're simply manipulating aerodynamic forces. Lift vector, drag. Vector, slip angle, induced drag reduction. The mathematics work regardless of what the aircraft designers intended. 12,000 feet. The radio crackled. A new voice, military, professional, carrying barely contained excitement. Viper, this is Reaper. We have visual on your aircraft. For F-22's information with you. Confirming visual observation of asymmetric flight configuration. Ma'am, you're flying that Embraer in a configuration that shouldn't be stable. But it is. How are you doing this? Helena keyed the radio. Reaper, physics doesn't care about certification standards. I need terrain assessment for landing site. Copy that, Viper. Scanning terrain now. Stand by. To the passengers in the cabin, the view out the windows had become surreal. For F-22 Raptor fighter jets were flying in formation with them. Sleek, lethal-looking aircraft with swept wings and twin tails, keeping perfect position alongside the gliding regional jet. Some passengers were filming on their phones. Others were praying. Some were too terrified to look. 8,000 feet. Reaper's voice came back, "Viper, I have a potential landing site. Interstate 40 runs through a valley 3 miles ahead of your current position. 4 miles of straight road. We're making low passes now to clear traffic." Helena responded, "Copy. Sarah, you're going to land on a highway." Sarah's voice broke slightly. "I've never landed on a highway. I've never landed anywhere except airports. I don't know how to." Helena interrupted, her voice firm, "You know how to land an aircraft. The principles are identical. You're simply landing on asphalt instead of concrete. The highway is 60 feet wide, your wingspan is 85 feet. You'll have no margin for error, but it's sufficient. What if there are cars? What if there are obstacles? Reaper's F-22s are clearing the highway now. Trust them. Trust your training. And trust my mathematics. 5,000 feet. Deploy landing gear. Execute now." Sarah pulled the landing gear lever. The familiar 3 green lights illuminated: nose gear down and locked, left main gear down and locked, right main gear down and locked. The aircraft slowed dramatically as drag increased. The descent rate increased slightly. Descent rate 1,500 feet per minute. Forward speed 160 knots. Glide angle approximately 6 degrees. Helena's voice carried confidence. "You're going to make it to the highway. 3,000 feet. The F-22s dove ahead of the Emperor, screaming down Interstate 40 at 500 feet altitude. Reaper and his wingmen made multiple passes, their afterburners creating thunder that echoed through the valley. On the highway below, cars scattered. A minivan swerved onto the shoulder. A pickup truck braked hard. An 18-wheeler tried to stop, jackknifing across both lanes. State police cars were already responding, having been alerted by air traffic control. They were setting up roadblocks, stopping traffic, clearing the emergency landing zone. 2,000 feet. Helena could see the highway clearly now through the cockpit windscreen. A straight ribbon of gray asphalt cutting through the forested valley. The jackknifed truck was being pulled clear by a police tow truck. "Sarah, you can do this. Listen to my voice. Follow my instructions exactly." 1,000 feet. The highway filled the windscreen. Helena could see individual lane markings. A guardrail on the left side. Trees on both sides. The asphalt looked rough and patched. At 100 feet altitude, you're going to execute the following sequence in order: retract left flap to neutral position, retract right spoilers completely, neutralize aileron input, level your wings. You will have approximately 5 seconds of conventional flight characteristics before touchdown. Use those 5 seconds to flare and land. Sarah's hands were positioned on the controls, ready to move. Her breathing was fast and shallow. Marcus was gripping the sides of his seat, his knuckles white. 500 feet. The F-22s pulled up hard, climbing away to give the Emperor clear airspace. Reaper's voice: "Runway is clear, Viper. You're cleared to land." 200 feet. Trees were flashing past on both sides. The highway was rushing up to meet them. Helena could see cracks in the asphalt. A road sign. The centerline. 100 feet. Now. Execute. Flaps neutral. Spoilers retracted. Level wings. Sarah's hands moved in a blur of practiced motion. Flap lever to neutral. Spoiler switch off. Control yoke rolled right to level the wings. For exactly 5 seconds, the Embraer E-175 flew like a normal aircraft. Sarah pulled back gently on the control yoke, flaring the nose up to reduce descent rate. The main wheels kissed the highway surface. Hard. Bouncing once. Slamming down again. The tires screaming. The nose wheel touched down, slamming into the asphalt with bone-jarring force. Sarah stood on the brakes with both feet. The tires smoked. The anti-skid system pulsed. The aircraft decelerated hard. They rolled down Interstate 40, a commercial airliner on a highway, for 3,200 feet before finally stopping. 76 souls, alive. For a long moment, nobody in the cockpit moved. The aircraft was silent except for the sound of Sarah and Marcus breathing heavily. Then Marcus started laughing. Hysterical, relieved, disbelieving laughter that shook his whole body. Sarah was crying, tears streaming down her face, her hands still gripping the control yoke even though they'd stopped. Helena was staring at her hands. They were shaking now. The adrenaline crash was hitting hard. For the entire emergency she'd been completely calm, her mind clear and focused on physics and procedures. Now that it was over, the reality of what they'd just done was sinking in. They'd flown a commercial airliner in a configuration that violated every certification standard. They'd gambled 76 lives on a theoretical procedure that had never been tested in real conditions. They'd landed on a highway. And it had worked. Behind them in the cabin, chaos and celebration erupted simultaneously. People were crying, laughing, hugging each other, shouting with joy and relief. The flight attendants were trying to maintain order, preparing to evacuate the aircraft. Sarah finally found her voice: emergency evacuation. Deploy the slides. Get everyone off this aircraft. There's jet fuel everywhere and we're sitting on a highway with traffic. She activated the emergency slide system. The doors popped open with explosive charges. Inflatable slides deployed from the front and rear exits. Helena stood up slowly. She felt disconnected from her body, like she was watching herself from outside. Marcus grabbed her hand. Dr. Voss. Helena, thank you. You saved us. You saved everyone. Helena pulled her hand free gently and walked out of the cockpit without responding. The cabin was a scene of controlled chaos. Flight attendants were directing passengers to the exits. People were sliding down the emergency slides onto the highway asphalt. Some were filming everything on their phones. Others were just standing and sobbing with relief. Several passengers tried to hug Helena as she walked past. She moved through them without making eye contact, stepping over bags and belongings scattered on the floor. Down the emergency slide. Onto the asphalt. The highway stretched in both directions, now completely blocked by the Emperor sitting in the middle of both lanes. State police cars were everywhere, their lights flashing. Ambulances were arriving. Fire trucks with foam systems ready in case of fuel fire. And then Helena saw the F-22s. They had landed on the highway behind the Emperor, a formation landing that must have required incredible skill. For fighter jets sitting on Interstate 40 like it was a normal runway. Reaper was running toward her, still in his flight suit and helmet, and Helena saw that he'd already removed it. Viper. That was the most incredible flying I've ever witnessed. You actually did it. Protocol 7 works. You proved. He stopped talking when he saw Helena's face. She was pale. Shaking. Her eyes were unfocused. She walked past him to the highway guardrail and sat down heavily. Her hands wouldn't stop shaking. She'd just gambled 76 lives on a procedure that had a 34% success rate. 34%. That meant 66% chance of catastrophic failure. She'd convinced 2 pilots to fly their aircraft in a configuration that could have failed at any moment. One wrong control input. One unexpected gust of wind. One miscalculation in her mathematics. Everyone would have died. But they hadn't. This time they'd gotten lucky. And then Helena heard approaching footsteps and looked up to see a man in an FAA jacket approaching with a clipboard and a very serious expression. Dr. Helena Voss. Helena looked up slowly. I'm Senior Investigator James Chen, Federal Aviation Administration. I need to ask you some questions about what just happened on that aircraft. I saved 76 lives using emergency procedures based on established physics principles. Chen's expression didn't change. Dr. Voss, you commanded pilots to fly a commercial passenger aircraft in a configuration that violates every FAA certification standard. You used experimental procedures that have never been tested or approved. You took control of an emergency situation without proper authority. You directed an aircraft to land on a highway in the middle of active traffic. You put 76 lives at risk with unproven techniques. Reaper stepped between them, his voice sharp with anger. Excuse me? She put lives at risk? Those people were already going to die. The aircraft had dual-engine failure over mountains with no airports in glide range. They were going to crash. She saved them using procedures she designed based on years of research and test flight experience. Procedures that worked. Major, I understand your loyalty, but this is a civilian matter that requires investigation. Dr. Voss used to work for the United States Air Force as a civilian contractor, Reaper interrupted. She designed the emergency procedures that are currently in use in every F-22 and F-35 in our inventory. What she just did proves everything she was trying to teach us. Maybe instead of investigating her for saving lives, you should be learning from her techniques. The other 3 F-22 pilots had joined them now, creating a protective circle around Helena. For combat pilots in flight suits, standing between their former instructor and the FAA investigator. But Helena wasn't listening to any of it. She was thinking about Test Flight 341. About Major Torch nearly dying because her test protocol pushed systems beyond their limits. About being called reckless by the Air Force Investigation Board. She'd just proven her theories worked in real-world conditions. She'd proven that Protocol 7 was viable. She'd proven that her mathematics were correct. And it didn't feel like vindication. It felt exactly like Test Flight 341. She'd created an emergency to prove she could solve it. Except this time, she hadn't created the emergency, but she'd still gambled lives on theoretical procedures. What if her calculations had been wrong? What if the asymmetric configuration had become unstable? What if a crosswind had hit them during the highway landing? Everyone would have died. And it would have been her fault. She'd proven she was right. But she'd also proven she was willing to bet everything on being right. That wasn't engineering. That was gambling. The FAA investigation took 6 months and was exhaustive in its scope. They examined every second of United Express Flight 4422. They downloaded the flight data recorder and cockpit voice recorder. They interviewed Sarah and Marcus for dozens of hours. They interviewed passengers. They interviewed Reaper and the other F-22 pilots. They interviewed Helena for 3 separate sessions, each lasting over 8 hours. They ran computer simulations of the asymmetric flight configuration. They consulted with aerodynamics experts from MIT, Stanford, and Boeing. They brought in test pilots from the NTSB to evaluate whether Protocol 7 could be safely taught. The lead investigator, James Chen, spent 6 months reviewing every detail. Their final conclusion was complex and carefully worded. Dr. Voss's emergency procedures were not certified by the FAA, were not tested in controlled conditions, and violated numerous regulations regarding commercial aircraft operation and flight. Envelope protection. The asymmetric flight configuration created during the emergency is not permitted under any current certification standard. However, the investigation acknowledges that given the specific circumstances of United Express Flight 4422, dual-engine failure caused by fuel contamination, no possibility of engine restart, no suitable landing areas within standard glide range, and imminent terrain impact, conventional emergency procedures would have resulted in controlled flight into terrain with total loss of life. Dr. Voss's intervention, while technically in violation of multiple FAA regulations, resulted in 0 fatalities and 0 serious injuries. The procedures she employed, while unorthodox, were based on sound aerodynamic principles and extensive computer modeling. The FAA does not approve these procedures for general use or training. Commercial aviation must continue to operate within certified flight envelopes and follow established emergency procedures. Dr. Voss's actions were specific to an extraordinary circumstance and should not be interpreted as approval for similar techniques in other situations. Translation: She broke every rule in the book, but she saved everyone, so we can't punish her. But don't anyone dare try this again. The FAA issued an official statement to the press. The successful outcome of United Express Flight 4422 does not constitute approval of non-standard flight procedures. While we acknowledge Dr. Voss's expertise and the positive outcome in this specific incident, commercial aviation safety depends on adherence to established, tested, and certified procedures. Captain Sarah Lynn and First Officer Marcus Webb were praised publicly for their skill and composure under extraordinary pressure. They appeared on morning news shows. Were interviewed by aviation magazines. Were called heroes. Both received commendations from their airline and were invited to speak at pilot training conferences. Helena refused all interview requests. Refused to appear on any news programs. Refused to attend any award ceremonies or recognition events. When the airline offered to fly her anywhere in the world as thanks for saving their aircraft, she declined. When Lockheed Martin approached her about returning to work, she sent a one-sentence email: "No." The only public appearance she made was 6 months after I-40, when the NTSB invited her to present her findings to a closed-door session of aviation safety experts and senior pilots from major airlines. She showed them Protocol 7 in detail. Explained the physics step by step. Demonstrated the computer simulations. Showed them the mathematical proofs. An FAA official raised his hand: "Dr. Voss, given the success of your procedure, should we be incorporating these techniques into commercial pilot training?" Helena's answer was cold, precise, and final. No. You should not be teaching this to commercial pilots. You should be designing aircraft with sufficient redundancy that pilots never need these techniques. Better fuel quality control to prevent contamination. Better engine restart procedures. Better glide performance. Better emergency power systems. But you won't do that, because it's expensive and because these failures are statistically rare. So eventually, another aircraft will experience dual-engine failure in a situation where conventional procedures won't work. When that happens, pilots should know that physics doesn't care about FAA certification standards. The aircraft doesn't know what's in the flight manual. It only knows lift, drag, weight, and thrust. Use what works. Manipulate the forces available to you. Survive. Then demand better aircraft so no one else has to be desperate. She walked out of the meeting and never attended another aviation safety conference. Helena didn't return to Lockheed Martin despite multiple offers. They'd contacted her apologetically several times. Dr. Voss, in light of recent events, we believe our previous termination decision may have been too hasty. We'd like to discuss bringing you back in a senior role. Director of Emergency Systems Research. Significant salary increase. Your own research team. Helena's response was a polite email: "Thank you for the offer. I'm not interested in returning to test flight operations. Best regards, Helena Voss." She didn't become a celebrity systems engineer. Didn't write a book about I-40. Didn't start a lucrative consulting company. Didn't do TED Talks or keynote speeches. Instead, she did something completely different and entirely unexpected. She created an open-source database called the Emergency Flight Control Protocol Library and published it online for free. The website was simple and professional. No advertising. No paywall. No login required. Just pure information. It contained hundreds of detailed recovery procedures for scenarios that supposedly never happen. Contaminated fuel dual-engine failure procedures, asymmetric control surface failure recovery, multiple simultaneous system cascade protocols, terrain avoidance, gliding techniques for mountainous regions, highway and road landing procedures with traffic clearance guidance, emergency descent procedures and various terrain types, techniques for flying aircraft outside certified flight envelopes, crosswind landing with degraded flight controls, water ditching with control surface failures, many others. Each procedure included detailed physics explanation, step-by-step implementation instructions, computer simulation results with success rate percentages, known risk factors and failure modes, warning labels about certification status, links to academic papers supporting the techniques. The website had a simple disclaimer at the top. These procedures are not approved by any aviation authority. They violate certification standards and operating limitations. They should only be used in emergency situations where conventional procedures have failed and no other options exist. Use at your own risk. The mathematics are sound. The physics work. But these are desperate measures for desperate situations. Airlines officially rejected the database. FAA guidance to commercial carriers was clear. The Emergency Flight Control Protocol Library contains procedures that are not certified for use in commercial aviation. Airlines should not train pilots using these materials. But pilots downloaded it anyway. Thousands of them. They studied it quietly. Discussed it in private online forums. Debated the techniques in chat groups. Some criticized Helena. These procedures are dangerous. She's encouraging pilots to violate safety regulations. Others defended her. She's providing information that might save lives someday. Knowledge isn't dangerous. Ignorance is dangerous. 2 years after I-40, something happened that validated Helena's work. A cargo pilot named Robert Hayes was flying a Boeing 737 over the Brooks Range in Alaska, remote mountains, no airports, harsh weather. His aircraft lost all hydraulic systems due to a catastrophic failure in the central hydraulic reservoir. No flight controls. The aircraft was essentially a missile flying at 400 knots toward mountains. Robert Hayes had read Helena's database. He'd studied her asymmetric mountain descent protocol. He'd never practiced it. Never trained on it. But he'd read it and understood the principles. He used differential engine thrust to control yaw. Used asymmetric flap deployment to control pitch. Found a frozen lake and landed the 737 on ice. Everyone survived. Robert tried to contact Helena to thank her. He sent emails. Left phone messages. Tried to reach her through Lockheed Martin. Helena never responded. 5 years after I-40, experimental test pilot schools started quietly incorporating modified versions of Helena's protocols into their advanced training curriculum. Not commercial schools, experimental and military test pilot programs. 10 years after I-40, some of her procedures were officially incorporated into F-22 and F-35 emergency training, though they carefully avoided mentioning her name in the official documentation. But Helena never flew again. Not in the back seat of a fighter jet. Not in simulators. Not even as a passenger on commercial flights. She'd flown on United Express Flight 4422 from Charlotte to Pittsburgh, and that was the last time she'd ever been in an aircraft. People asked her why she wouldn't fly anymore. She never answered. But the reason was simple. Every time she closed her eyes, she was back at 5,000 feet over Interstate 40. Gambling 76 lives on theories she'd only tested in computers. Telling 2 terrified pilots to fly their aircraft in a configuration that could have failed at any moment. She'd proven she was right. Her mathematics were correct. Her physics were sound. Protocol 7 worked. But she'd also proven something else. She'd proven she was lucky. The asymmetric configuration could have become unstable. The pilots could have overcorrected a control input. An unexpected crosswind could have hit them during the highway landing. The spoilers could have created too much drag. The flaps could have stalled the left wing. 1,000 things could have gone catastrophically wrong. They didn't. This time. They got lucky. But this time wasn't good enough for Dr. Helena Voss. She was an engineer. Engineers don't rely on luck. They rely on redundancy, safety factors, tested procedures, proven designs. She'd saved 76 people by gambling that her untested procedure would work. And it had worked. But it shouldn't have been necessary. The aircraft shouldn't have had contaminated fuel. There should have been better fuel quality control. Better engine restart procedures. Better emergency protocols. She'd proven that desperate measures could work in desperate situations. But aviation shouldn't be desperate. 3 years after Interstate 40, a graduate student named Jennifer Park from MIT's Aerospace Engineering Department tracked Helena down. Jennifer was writing her dissertation on unconventional emergency flight procedures and desperately wanted to interview Dr. Voss. After 6 months of polite persistence, Helena finally agreed to answer questions, but only in writing, via email, no phone calls or video interviews. Jennifer sent her questions. Helena's responses were characteristically precise and brutally honest. Question: do you consider yourself a hero for saving United Express Flight 4422? Helena's response: no. I consider myself lucky, and I consider the outcome fortunate. Heroism implies deliberate courage in the face of danger. What I did was calculate probabilities and make recommendations based on physics. The pilots, Captain Lin and First Officer Webb, were the ones who executed the procedures under extraordinary stress. They deserve any credit for heroism. I designed protocols to save lives when everything goes wrong. They worked once, in one specific situation. That doesn't make them safe. That makes them desperate. Aviation should never be desperate. We should design aircraft with enough redundancy, enough safety systems, enough backup procedures that no pilot ever needs to use asymmetric gliding techniques or land on highways. But we don't live in that world. We live in a world where profit margins matter more than redundant systems. Where statistical probability of failure is considered acceptable if it's low enough. Where good enough is the engineering standard instead of impossible to fail. So impossible situations will happen again. Systems will fail in ways that weren't anticipated. Pilots will face scenarios they weren't trained for. When they do, I hope they remember this: physics doesn't care about certification standards. Physics doesn't care about what's written in the flight manual. Physics is mathematics. It's lift and drag and thrust and weight. It's control surfaces and airflow and energy management. Use what works. Manipulate the forces available to you. Think like an engineer, not like a checklist follower. Survive. Then demand better aircraft. Demand better training. Demand better safety protocols. Demand redundant systems and foolproof backups. Demand a world where no one ever has to choose between following the manual and surviving. Question: would you recommend your Protocol 7 be incorporated into commercial pilot training? Absolutely not. Protocol 7 was designed for an impossible situation. It worked once. That doesn't mean it's safe or reliable. Commercial aviation should focus on preventing the situations where Protocol 7 would be necessary, not training pilots to use it. Better fuel quality control. Better contamination detection. Better engine restart systems. Better glide performance. Better emergency landing site identification. Prevention is better than recovery. Question: do you regret developing these procedures? I regret that they were necessary. I don't regret making the knowledge available. Knowledge itself is neutral. How it's used determines whether it's beneficial or harmful. I've made my research freely available because I believe pilots deserve access to information that might save their lives someday. But I also hope that information never needs to be used. Question: why did you stop flying? Helena's response to this question was notably shorter. Because I proved I was willing to gamble lives on being right. That's not engineering. That's recklessness. I don't want to be that person. The dissertation was published. Helena's responses were quoted extensively. The paper received attention in aerospace engineering circles and was discussed at several conferences. Helena never read it. She'd moved on to other work, designing improved fuel contamination detection systems for a small aviation technology startup, working remotely from her home in Vermont. 15 years after Interstate 40, United Express Flight 4422's route from Charlotte to Pittsburgh was still operating, though with different aircraft and different crews. A young aerospace engineer named David Chen was flying that route for a job interview. He was 25 years old, nervous, excited. This was his dream job, flight systems engineering at Lockheed Martin Skunk Works. He'd requested seat 12F specifically. The flight attendant noticed when she checked his boarding pass. She was an older woman now, had been flying this route for 20 years. Her name tag read Jennifer. Seat 12F, she said with a knowing smile. That's a special seat. Do you know the story? David nodded enthusiastically. Dr. Helena Voss sat in that seat when she saved this flight 15 years ago. I know everything about it. I studied her open-source protocols in graduate school. I wrote my thesis on asymmetric flight control recovery techniques. She's the reason I became a systems engineer. Jennifer's smile widened. Really? What was your thesis about? Improving Protocol 7 with modern fly-by-wire systems. Dr. Voss designed her procedures for aircraft with mechanical controls. I theorized that electronic flight control systems could execute her asymmetric configurations more precisely, increasing the success rate from 34% to potentially 61%. Did you ever try to contact her about your research? David shook his head. I tried. Sent emails. Left messages. But she doesn't respond to anyone. I understand why. She proved her point and moved on. She doesn't want fame or recognition. She just wanted to make the knowledge available. Jennifer poured him water. What did you learn from studying her work? David thought carefully before answering. That being brilliant isn't enough. That being right isn't enough. Engineering is about preventing disasters, not just solving them. Dr. Voss proved that impossible situations can be survived with the right knowledge. But she also proved that we shouldn't put people in impossible situations in the first place. That sounds like something she would say. Her final public statement said that we should demand better aircraft so no one has to be desperate. That stuck with me. That's what I want to do with my career, design systems that don't fail. Redundancy. Safety. Prevention. The flight continued normally. Both engines ran perfectly, as they almost always did. They landed in Pittsburgh without incident. David got the job at Lockheed Martin. His first project was exactly what he'd hoped for, improving fuel contamination detection systems to prevent dual-engine failures like the one that nearly killed 76 people 15 years ago. He never met Dr. Helena Voss. She lived quietly in rural Vermont, maintaining her open-source database, consulting remotely on aerospace safety projects, and carefully avoiding any situation that might put her back in an aircraft. But her work continued. In the protocols that pilots studied and hoped they'd never need to use. In the young engineers she'd inspired to prioritize safety over profit. In the aircraft systems that were designed more carefully because someone had proven that desperate situations could be survived. Dr. Helena Viper Voss had sat quietly in seat 12F, working on her laptop, ignoring the world around her. Just another cold business traveler that everyone immediately forgot. Until 76 people needed someone who understood that physics doesn't care about flight manuals. She'd saved them all with mathematics and procedures that shouldn't have worked but did. Then she'd made sure that what she'd done would never need to be done again. Because the greatest engineering triumph isn't solving impossible problems. It's preventing them.